Yeah, this is here. This is where we ended last time. We were talking about the drivers. Of course, you played with the drivers in lab yesterday, so you should be good, right? Remember, the driver is like basically a switch. Do I allow the signal through or not? That's it. If it doesn't, then you don't get a 0. Remember, a 0 is not the same thing as the absence of a 1, okay? A 0 is not a 1, and a 1 is not a 0, but there's that high impedance state, which is neither, okay? That's important. Oops, all right. And then we talked about the RAM symbol here that we were going to play with. There's 2 versions that ultimately act the exact same way. DIN. This one has 2 data lines. One is for input, one's for output. This one can only read input if it's coming in from this line. This one can only output to that line, where this one can read or write on that line, depending on the state of like whether I'm storing or I'm, I don't know what, load from RAM, I don't know, whatever that is, but depending on what the control lines are, okay? And you can say, wow, they're so different, but they're not really, because you can hook, like these 2 things are often hooked up to the exact same one line in the end. And if they are hooked up to, like, let me show you what I mean. Memory, RAM, separate ports. Often they're hooked up in something that looks effectively like this. You know, and this line's going, who cares? It doesn't really matter, right? You're like, oh, okay, in and out. But, I mean, we could have just drawn the box here and then, oh, there's only one data line, right? It doesn't really matter. It's just, am I reading or writing? That's controlled by the store or LD. Let's have a look. What does LD say? If the input is high, the output is active and the data is visible. Yeah, I'm guessing it's like load from RAM and store into RAM. I'm guessing that's what that is, but I don't really know. Okay, cool. Yeah. All right. Now, these concepts aren't going to be entirely new. We've talked about this a little bit, and we played around with this in lab as well. So there's this idea of a bus. That is, and there's different types of buses, but there's this idea of a bus where some common signal is used to transfer data around the system. So we've been talking about RAM, and we also talked about a register, effectively, right? We talked about the registers, which when you kind of like stack the registers, you get RAM, but you know, RAM and registers. But we could have RAM. Imagine we've got this like giant signal line. Like this, and you're gonna have all these different components coming off of this signal line. And these components need to maybe receive data or output data, like RAM. And we might have a register, which we will see an example of just that in a moment. But there's other components of the system that are going to need to move data from this component to that component, and then that component to this component, and then that component to, it's going to move data around. And the signal lines, the wires connecting all this is called the bus. But there are different types of buses. They all kind of do the same general thing, and often people will just say bus, and based on the context, you'll know what we're talking about specifically. But we've got a data bus. That's the bus that transfers data around. And we can also have something called an address bus, which is sometimes a separate bus. Sometimes it's the same physical bus. But the address bus transmits memory addresses around the system. and a control bus. This is a series of signals that are used to control which components are outputting and inputting and whatnot. We're going to see a concrete example of this very shortly. So as discussed before, we have this tri-state logic. We use these drivers to control the output of RAM. And to review this again briefly, if the driver is like on, it relays whatever the input signal is. If that input signal is a 1, we output a 1. If it's a 0, we output a 0. Okay? But if that if the control line for that buffer is off, it doesn't output anything. It outputs Z, which is not outputting anything, but we can think of it as like, oh, it's a Z state. For a shared signal line like a bus, this is extremely important because if this is outputting data and this is outputting data, we've got a problem. Here, can you see that? Right? If this is outputting data and this is outputting data, we've got a problem. Only one thing should be writing to the bus at any given time. Putting data onto the bus at any time, only one. We kind of talked about this before, because imagine this was outputting a 1, which means connect to some voltage source. And this is outputting a 0. That means connect to ground. Well, now we've got a voltage source connected directly to ground effectively. That doesn't make any sense, right? So we need to be very careful about when components are actually putting data onto the bus. And a driver is a great way to deal with that. For a shared signal line like a bus, it's important to only have one component outputting at a time. Outputting 0 is not the same as outputting nothing. Remember, that's an important thing, like we've said several times already today. Outputting a 0, pardon me, I've got to keep an eye on my phone because I might get a phone call that I might need to actually take, so I apologize for that. If I do, someone remind me to take the mic off. Otherwise, you'll hear me talking about my furnace on the video. All right. Yeah, so outputting a 0 is not the same thing as outputting nothing. Z is like nothing. 0 is connect to ground. It's a different thing. So in other words, if two components are connected to the same output line, if one component's outputting 0, it's connected to ground, the other one's connected to 1, we've got a problem. And then there would be no voltage on the line because it's connected directly to ground, which creates like a short circuit, and that's a problem. We could think of an analogy, right? So this is a sink. Okay, think of this as like a top-down sink, okay? You know what I mean? Like these are the drains, these are the faucets, okay? So we've got a long sink, okay? Each of these faucet drains would be like a connection to, like this is for RAM. These are not like different these are not different bits. Okay, that's not what we're thinking here. This would be like, okay, this is, maybe RAM is outputting information. Water would be coming out of that faucet. If RAM is reading information, water would be, like that drain would be open and the data could flow into that drain. Okay, cool? And maybe this is register. Maybe this is like some mechanism to add information. This is some place we could put data to output it. There are all these different components we're going to learn about. But we have all these components connected to the bus. The sink is the bus. If I want to put data onto the data bus, right? If RAM is outputting data, and this is like some output register where it can like output, like display data, I want this faucet on, and this faucet, this drain open, okay? All of the other ones, all of the other components, if we add water, we're going to have a problem, right? Because I want only the data from RAM, from this component, to go to that output register. If we, all the other components, the faucet should be off and the drain should be closed. It's doing nothing. Okay? That's the idea. Okay, the sink represents some shared signal line that several components can connect to. The components' connections to the signal line are represented by the faucets and corresponding drains. If a component is outputting a signal to the shared line, the faucet will be either on or the drain will be open. When the output is 1, that's like the faucet is on, and water is being added to the sink. And when the output is 0, the drain will be opened, allowing any residual water to drain from the sink. All the components will be left alone, Z, with neither the faucet or the drain open. Okay, like we were just saying. If one component connects, oh, sorry, okay, cool. Low. The presence or absence of water in the sink means that the signal is high or low, respectively. Consider what would happen in the analogy if one tried to use 0 to mean nothing. All the drains were open, right? If 0 meant nothing, the drains would be open, and as soon as you turn on a tap, like that water disappears. It's gone, right? No good. This would be a problem since the sink should have water in it. The water that we want to go specifically to whatever component. I think maybe I got that analogy wrong. I may have told that story wrong. I think I did. Forget everything I just said. Let's start again. I got it wrong where I was saying this, oh, it's outputting information. No, this would be like if this component is outputting a 1, the drain is, the sink is, the faucet is on. If it's outputting a 0, the drain is on. That's not what it is. It's not input, output. Both are states of what data is it putting onto the bus. If I want to put data onto the bus, I turn on the faucet. Okay? So then the water can fill up. If I want to make sure there's no data on this line, what do? I open the drain. Like if I want to output a 0, meaning that there's no data, like there's 0, there's no water there, I open the drain. Now there's no water in there. Okay? If I want to output data from here, okay, but I leave all of these other things as like, oh, I'm outputting nothing. Let's open the drain. 0 means nothing, which it doesn't, right? That's the problem. Then no water would ever fill up. Like whatever signal is that I really want can't be there. I think I made it, I think the analogy just didn't land now because I messed it up the first time. The real question I have is, do you understand the general idea of the Z state? Okay? We are outputting a 0, we are outputting a 1, or we are outputting nothing. Okay?
We're thinking the openness of the drain requires that the tap is on, I think?
No. No. It's, if this is RAM, do I want to output a 1? If I want to output a 1, I turn the tap on. Do I want to output a 0? I want to sink that line, meaning I open the drain. That's what I want, yeah. That's what it is. If you're left going like, wait, what? Yeah, I messed the analogy up the first time and now it's conflicting. It doesn't matter. All that matters is that we understand that the Z state is this like third state. And we know why it's important. Because 0 is not the absence of a 1. 0 is connected to ground. Connect to voltage source, connect to ground, or nothing. No signal. Okay? And it was visually represented as like a gray line. It's very important that we don't ever try to put multiple outputs onto the bus at the exact same time. That's the key thing here. Because if we do, we're going to have a problem. So, I'm going to click this. No, back. Here is a design. Have a look at this. Let's just do that. Okay? What do we have going on? Actually, no. I'm going to give you 30 seconds. Look at this. Try to make sense of what's going on, and then we're going to talk about it. I'll give you that you are absolutely capable of understanding what's happening here. All right. So, first, over here is what, in fact, maybe I even have pictures, a follow-up picture. Yes. So, all right. Here is what I'm going to call my data bus. All right? I can toggle these buttons. However, these buttons are actually tri-state buttons. I can either put a 1 on it, a 0 on it, or nothing. That's going to be very important. And I'll show you examples of why it's important as we go. So this is a data bus. Okay, I can put data onto this signal line, and then this is a 4-to-1 merger. And then down here, all I have is just like the opposite, right? A 1-to-4, and then I'm just showing the output, right? So if I go here and toggle these things, these will light up accordingly, okay? Yeah? But there's more components here, and these components can output information to this line as well. Meaning those could be, we could have this in a state where all of these are off in a Z state, and these could still be on depending on what data is in here. We'll see examples of this as we go. So this right here is like our data bus. Here, this is a RAM component with a single data line. This is a register. And the register has a driver here to control when it's actually outputting. Because if you remember back to when we were playing with registers, registers were always outputting their data. Whatever data was stored, it was always outputting it. So we want a little bit more control over when the register is actually outputting the data, so we just throw a little driver on there. And we can turn it on or off. We've got a clock signal down like this. It's connected to the clock on the components that need a clock, both of them. And then we have 2 control lines here for RAM in. When do I want to put data into RAM? And then RAM out. When do I want to output data from RAM? Similarly for the register. I've got control over when I want to put data into the register, when I want to output data from the register to the bus. Okay? And then finally up here we've got 2 signal lines to control which memory address in RAM I actually want to read or write to from, right? So we've got a bunch of different components here now connected to the same thing. Up until now, we've only looked at we built some logic circuits where we controlled inputs and outputs. We built registers, latches, and RAM. But we were always dealing with individual components. Now, I want to control multiple components at the same time and have them interact with one another. I have 4 data lines and 2 input lines. Can anyone tell me what would the shape of this RAM be? A box, yeah, sure. But maybe my question's unclear. Remember how much data can be stored in each memory address based on what you see here? What would you guess? In total, yeah. So each row, each memory address can store how many bits? 4. Why? Well, it's a pretty good guess based on the design of this, right? Because I can only put 4 pieces of data in there, 4 bits. And then how many rows are there? Well, here I've got 4. Why? Well, because I only have 2 address lines and I can only address 4 unique things, 0, 1, 2, 3, right? The fact that it's 4 by 4, that does not need to be even. This could have been 4 by 8. This could have been 8 by 4. Well, yeah, and so on and so on and so on. But I've just got it 4 by 4 for simplicity. I keep seeing emails pop in and I'm freaking out. All right, so. Yes?
Is the clock line considered
I guess kinda, but I've never really heard it referred to as a bus. It's just the clock, but I guess it kind of is because all the components should be hooked up to that same thing, but it's only ever like the clock. Yeah. But I suppose, yeah, that's an interesting observation. It kind of is like a bus, right? This is a line that carries the clock signal. So it's like the clock bus, kind of, yeah. Pardon?
For one thing, so it's like
Yeah. And the data is only ever going to go one direction. So there's no like reading or writing, right? We're not going to output information back to the clock, but anyways. Any other questions about what we see here? Based on, okay, what do we have down here? Okay. Let's see. All right. Above is a RAM component connected to a register component via a data bus. With this configuration, data can be input into the system via the input buttons, the memory address, the RAM components is the memory address the RAM component is referencing is controlled by the address input buttons. Okay, that does make grammatical sense. Finally, the components are controlled by turning on, off their inputs and outputs via those like little control signals. Notice how the register only has an input enable on the component itself, and we had to actually add this driver to create that like output enable. Entirely fine, right? You can think of these two components as like one logical unit together, right? Input, output. And output is controlled by the separate driver. Here, how the component signal lines are connected is important, not the actual physical layout. What I mean by this is the fact that RAM is up here and the register is down here and the data lines are over there and the control signals are over here. And that's entirely, we can move these things around. That doesn't really matter. All that matters is that they're hooked up this way, okay? I just thought this was a nice layout. Okay, the location, okay. Within the layout are three physical separate buses. The data bus, the green area, the address bus, which is only ever connected to one component here, but this could be different. And then we have got this like the control bus, which there's only 4 lines here, but this really is like the control bus, okay? These are the control signals, control lines, control, control, control. Address, memory addresses, memory addresses, memory addresses, and data, 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 okay? So what do we here? For transferring data between components, yeah, that's what the data bus is in this configuration. There are 4 data lines, but more could be added. The fact that I have 4 is just arbitrary. Data could be input in the system through the buttons. The data buttons are tri-state, and the output of the button can also be seen at any given time. These, of course, are not necessary. They're just there for us, so we can see, okay, what data is actually on the bus. You will notice that within digital, when you run this, like if I have the pattern like 1, 0, 1, 0, that's 10, right? 8, 9, 10, right? You would usually see on digital like OX0A or something. So like that means 10. It's a nice way to represent it. But I think it's nice to see like the bit patterns. So I like adding the output circles there. So here we go. Okay, the address bus controls which memory address RAM is currently looking at. This is for both reading and writing, right? If I want to write to memory address 1, these should be 0, 1. And if I want to write, that means I want RAM in. If I want to write or read from RAM, output from RAM, and I want to output memory address 2, I would say, okay, 1, 0, output. Okay? This just says, okay, what row are we looking at? What memory address are we looking at? And then this controls, are we going in or out? That's what that's doing. Here, there's no address line. A register is just a register. Okay? How many bits can be stored in this register? It's not a trick question. Based on this layout, what would you guess? It's fine if you don't know. I just thought, you should be able to guess. It's not a trick question. The answer is simple. How many bits can be stored on that register? 4. How would you know 4? Well, assuming this is the correct configuration. Why 4? Well, if there's 4 data bits on this one line, it better store 4. If it didn't and I tried to hit run, digital would be like, mismatch. You said there'd be whatever, but there's so many and whatnot. Okay. And then the control bus controls when individual components are reading from or writing to the bus. Here, each label I or O to specify input, output. The way I like to do it is like input is into the component and out from the component. Some people, it could get confusing because it's all relative, right? If I'm thinking of the bus, input output's different, right? Am I inputting to the bus? Well, that would be outputting from RAM. So it's a relative designation, but by convention, I will be, the I and O I'm going to follow is from the perspective of the component. All right? So, how would we load data into RAM? Consider how we would do this. Well, we're going to need to manipulate a couple of things. We're going to need to manipulate the address lines, right? Which address do I want to store it into? I'm going to want to manipulate the data lines somehow. I've got those buttons, so what data do I want to put in there? I can control that line. And if I want to put data into RAM, I need to control the control signal. So there's a lot going on, but I can do that by manipulating those signals. Okay? In fact, now we'll revisit what I was about to say. So probably the best explanation with an example. Let's add the value 0001 to memory address 0. And then we're going to put the data 1000 to memory address 1. Okay? Why am I doing address 0 and address 1? Doesn't really matter. Why am I inputting the values 1 and 8? Doesn't really matter. I'm just doing that. Okay? So how would I do that? Well, here's how I would do it. Is I would configure, here's a convention we're going to follow. I'm surprised this is actually like this. Each row will correspond to one clock cycle. Okay? I include the C pulse, but in general, each row corresponds to a clock cycle. This is going to be important. So how would I want to configure all the bits? Well, I want to do RAM in, RM in. I know in the picture it was labeled RAM in, but there's only so much horizontal space, right? So deal with it. Same with the register, RG for register. Hopefully you can figure that one out. So we want RAM in to be high, RAM out better be low, the register better be low, the register better be low. Address line should be 00 because I just conveniently want to write to memory address 0 and 0. And the data I want to put into memory address 0 is 0001. Now, nothing will happen on the system until the clock pulses. All right? But again, each row corresponds to a single clock pulse. So if this is the configuration, then that data would be loaded in there. Similarly, if I want to then write the data 10008 to memory address 1, what would I do? Well, RAM in again, RAM out 0, reg 0, 0, address line 01, and the data should be 1000. Okay? Cool. And then again, now it actually gets stored. All of these bits would need to be configured this way. When the clock pulse happens, it gets stored. It's pretty cool. In fact, look at this. It's just zeros and ones. I'm talking about control lines that are just low voltages and high voltages, right? On or off. But at the end of the day, we're representing on and off with zeros and ones. At this moment, I want there to be a bit of a click for you about like, oh, everything in a computer is zeros and ones. How does that work? Like just like this. That's what's happening. Some of those zeros and ones are data. Some of them are address lines, which is just data. And then the control signals, which is also just data. But they're, depending on what we want that data to be doing, yeah. That's what's happening inside the computer. By the way, by doing this, we are programming this system. We are. I'm not being obnoxious with my terminology. That's what we're doing. So here's like showing how I would configure it, right? Okay, on, off, 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 on. And then similarly, same here, but change it to 1 and 1, 0, 0, 0. Cool, right? I think that's pretty cool. So if one wants to now verify, okay, did we store that information? What do you think we would do? Well, now what we would do is we don't want to read, or we don't want to write to RAM, we want to read from it. The registers we leave alone. Which memory address? 0, 0. And what should the data lines be? Z. I don't want to put data onto the bus, so I set it to Z. I don't want it to be a 0. I don't want to set it to a 1. I want to let it to a high state. Because the values that I put on here is information I'm putting onto that signal line. I don't want to put information on that signal line. I want RAM to. Okay? So how would that configure? Like that. And I think this is better with an example. So let's open. No, don't look at that. No, don't look at this. One of these must be that design. 4x4 RAM dig? No. Maybe it's in a different... Oh, I think it's under my bus. No. No. Layout. RAM register. Okay, yeah. There we go. Cool. So. Okay, what do we want to put into... Let's have some... I know I said 1, 0, 0, 0, and whatever, but what data should we put into memory address 0? Somebody tell me. Just give me a bit pattern.
6.
No, bit pattern.
0,
1, 0, 1. So that's 5, right? By the way, if you didn't notice, if you like shift bits to the left, right? That's called a bit shift. You double the number. 1, 0, 1, 0 is 10. Why does it double? Well, consider if you move every bit over 1, you double its value. And if you do that to every bit, you double the value. Like if I had the number 24 and I doubled each digit to 48, well, I doubled the number. That's the same idea, right? Now here we're doing it with the place because it's binary, but anyways, we're doubling the number. It's kind of neat. Anyways, so what memory address do we want to store this into? Let's do 0. So RAM in, clock pulse, there. Oh, and here's what I mean. See how there's a 5 there? It's because the number 5 is there. So let's now put 1, 0, 1, 0 into memory address 1. Now you'll notice that I've left RAM in high. That won't matter until the clock pulse, okay? So like I want to leave it high, so I'll leave it high. Clock pulse, there we go. And then what do we want to put in address 2? Let's put in 15, okay. Address 2, clock pulse. And address 4 or 3. There, we'll do, what number is that? 9, right? Clock pulse, cool. So now, I'll turn that off. Now, one thing that's neat though, by the way, is RAM in, even when RAM's in, nothing will get stored into RAM until the clock pulse. RAM out's a little different. RAM out will output to the bus before any clock pulse. And that actually makes sense because like imagine that we will do this in a moment. We want data to go from RAM to the register. The register will read on the clock pulse, right? So the data has to be there already. And how will it be there already? Well, the RAM can output like before the clock pulse. So now I'm not going to do it right now because I would crash this run here. So let's go back to 0. These are not tri-state because that won't really matter. These have 0, 0, 0, 0 on the bus. The number 0 is on the bus, the bit pattern 0, 0, 0, 0. If I output from RAM right now, if I click this button, I would crash it because I am outputting a 0, or inputting, output, whatever. I'm putting the number 0 onto here from here, and I'm trying to put, what did we put in here? 5. In memory address 0 is 5. I would also be trying to put 0, 1, 0, 1. It would get all messed up. So what do I have to do? It's important that I put this into the Z state. There. We can see it's the Z state. Cool. Now, when I hit output, we see 0, 1, 0, 1. Cool. Now, what can I do with this? Well, oh, here, and we can also just go have fun here. Like, okay, there we go. There's that one, and then there's that one. Right? Those are that's all the data we stored. But now, I want to put some data from, okay, what have we done so far? We put data into RAM, and now we've gotten data out of RAM. But for the fun of it, let's put data from RAM into the register. Not from me to the data lines to the register, but let's go from, okay, we went me to RAM, and then RAM to the register. So what memory address do we want to put into the register? You've got 4 to pick from. 0. Ah, come on.
3.
You picked the wrong one. 3, okay. Okay, we're going to output. Now, how do I put that into the register? Well, we input into the register. So the data on this here is 9. Right? So 9 is hanging out right here. Right here. On the bus. I clock pulse. Now, presumably it's saved in there. Well, let's check. Okay, turn that off. Turn that off. This won't matter. The state of this has no effect on this. Okay? Let's output. If we did this right, what should be output? 9. Cool. Let's go. Yeah. We are doing this by toggling these switches, these toggles. But these are just 0s and 1s. And 0s or 1s are what I'm throwing around here. So this can manipulate 0s and 1s, and we're manipulating this with 0s and 1s. It's pretty cool. If only there was a way to get itself to control itself, right? Wouldn't that be cool? Hold on to your hats. We'll get there in a couple of weeks. Anyways, okay, out. Cool. Now, let's say, okay, we had 9 stored in memory address 3. Let's go and put that 9 in memory address 1. Let's just overwrite what was in memory address 1, okay? Just for fun. So we want memory address 1. That's still Z. We want to output from here, so the number 9's there, and we're going to input into memory address 1 the number 9. What was in memory address 1? I think it was the number, no, it was 10. 0 had 5, didn't it?
1. Yeah, I know you have 1.
Yeah. I think 1 had 10, right? I did 1, 0, 1, 0. Okay, you know what? No, let's find out. Let's find out real quick. Memory address 1, yes, had 10. Hey. Okay. So we're going to output from here, input to RAM, clock. Okay, stop, stop. Now what's, okay. Based on this, 0 should have 5, right? 1 should now have 9. Yep. 4 should have 9, and 2 should still have 15. Cool. Cool. Look at that. So with the register, we have this like temporary spot, like this hand. So now with the RAM and the register, I can like move data around. It's pretty cool. Again, all controlled with these zeros and ones. We programmed this little circuit. There's no automated process here. We had to click that clock. But by following those bit patterns, what should those signals be? Clock pulse, we're able to go and like manipulate what's happening here, which is pretty cool. Now, what would happen if, so this is outputting data. If I click this, we're going to have a problem. Okay? Boom. Why? More than one output is active on a wire, causing a short circuit. That's what would happen. That's the importance of that Z state. Or just not only the importance of the Z state, well, yes, that clearly shows the importance of the Z state, why we need to control when this is actually outputting. But that's what would happen if we tried to do it, right? Similarly, we can rerun it. If I try to output to here, and yeah, there we go. Yeah. Now you might say, how come it wasn't unhappy? It was just conveniently that these were all 0, so there was no conflict. We just got really lucky, right? Here. Like, how come it's not crashing? Everything is outputting, like, data is getting added to the bus from the register, from RAM, and from here. What's going on? Well, I don't really know, but my guess is digital will only discover that there's a problem when the signals don't match. Everything that is being added to the bus is zeros everywhere. It only notices something's wrong when, like, uh-oh, something doesn't match. Which makes sense, I suppose. And isn't it nice? It's like, hey, red, there we go, problem. All right, it lets you know which one was the problem. So any questions about what we just observed?
I think the short circuit, there we go, happened when I think 9 was on it though, and I think when you turn the register on, I think output from the register, I think it was also going to be output 9 anyway.
Let's find out.
I think it was.
Let's for fun, right? Let's put just 1 into RAM 0 clock, okay? Now, out. So here it looks like it's, yeah. So was it 9? I can't quite remember.
Coming out
Of the register and,
something was happening, I don't know.
let's put 9 into there, RAM in, clock. Let's put it into the register as well, clock. And now let's output. Seems happy with 9. There must have been a conflict somewhere. Either way, it looks like it's only going to discover the short circuit when, like, there's a difference in the signal, right? Like, if everything's outputting 1, it's like everything's 1 on that line. I guess it's safe, right? Because I guess at that point there wasn't a short circuit created, right? But anyways. Cool. Any questions about any of this? I think that's pretty cool. Now we are like, look, everything we've done up until this point was computer science. But I feel like it's like at this stage, it's a little bit more obvious. How like, oh yeah, by manipulating these things, we can control how the data is moving around. It becomes a little bit more clear, at least more close. We're still several layers of abstraction away from like what we're used to programming, right? Don't get me wrong. But I mean, this is as close as we've gotten so far. Where we're headed, by the way, is we're going to make a fully functional, Turing-complete, like 8-bit computer that we can program. And ideally, I don't know if we're going to get there. I think we will. We're going to also build an assembler for it. Okay? What's cool about this is every piece of code you've written, let's talk like a traditional language like C. Okay? Newer languages have like a virtual machine, so there's a little extra layer there, but let's ignore that for a moment. Let's say it's C. Okay? With C, okay, you go back a long time ago and you want to program a computer, you are setting switches high and low, kind of like this, and you hit run. Now, that's a pain in the ass. So people started going like, okay, if I want to add, that would be, okay, the pattern 0101 means add. Why? Don't worry about it. And that would depend on the architecture of your system, right? But like, okay, that means add, and then what do I want to add? Well, this bit pattern and that bit pattern. That's kind of a pain. So people created assemblers, and assemblers are like slightly nicer, where instead of saying 0101 to add, you would say, okay, add. And add really is like a find and replace. Like your assembler is doing like a find and replace. Find the pattern, add, and replace it with 0101, right? That's all it's doing. But it's definitely a lot nicer to look at than like bit patterns. So that's, an assembler would take those like tags and turn it into machine code, the zeros and ones. Then the layer of abstraction after that was like programming languages like C, right? Where C could take more of a high-level language and turn it into like the zeros and ones. In fact, interestingly enough, there's tags for, or there's like options for your C compiler to say compile this to assembly. So you can compile it and then look at the assembly code. And then the assembly actually is like turned into the zeros and ones. Now you are used to working at a high-level language. Some people call like C a mid-level language. It's a high-level language, okay? Assembly is like a low-level language. C, high-level, they call it mid because like, oh, okay, you can get a little bit more control over it, so okay, it's less high than, it's nonsense. So we are going to work towards the assembly level in this course. Everything that you've been doing up until this point has been at the compiler level, where you write code and it gets compiled that runs on your machines. We're building the machine, and we're going to write our own assembly for it, which is really cool. Anyways, we're working our way towards there. Any last questions? All right, I'll see y'all later.